imaging technology for object recognition, or transparent cell observation, like a DIC microscope or dark field microscope. So transparent cell was very difficult to be monitored under bright field microscope. So, but here edge detection can help to check their morphology. So there are many prior arts which for this edge detection, but our first motivation was to make these electrical tunable metal lenses for dual mode imaging, like a simple imaging and also edge detection imaging. The design philosophy was exactly the same as the previous example. So let me skip it. And this is our device. We integrate our metal lens onto our liquid crystal cell. So here, by changing electric bias, you can change this focal point from this circular point to this donut-shaped beam. So yeah, this is imaging result. Simple imaging and edge detection imaging. All right, it works well. And our next goal was to monitor the transparency. So first we prepared this monocyte cell. So it has a circular shape. So it was quite, it has simple geometry. So between this simple imaging mode and edge enhanced mode, you can differentiate them. And also, so it was quite easy to differentiate. But next we prepared this 3D cell or sphere cell. So under the bright field microscope, it was quite a bit difficult to see their morphology. This cell morphology detection is important for this drug screening. Once you spread the drug, then their morphology will be changed. And for this aim, our edge enhancement mode will be effective. So this is bright field and this is edge enhancement mode image. The imaging quality was not that good, but this is because our lens setting was not that optimized. So focusing efficiency was quite low. But anyway, we firstly demonstrate this dual mode imaging. And this is the last topic. I want to apply our metal lens technology to this photoacoustic microscopy. This is another imaging modality. So this is similar to this lightning and thunder effect. So let's say there is a lightning, then air can absorb the light and then they're gonna expand. And if it goes back to the original position, then they're gonna emit the sound, the thunder, right? Similarly, in the body, same process takes place. If you're shining the laser, then the biological substance, you're gonna observe the light and it's gonna expand. And if it goes back to original position, then it's gonna generate ultrasound. So by measuring this ultrasound, you can reconstruct their shape. And also, this biomolecule, like a cell nucleus or a melanoma or a red blood cell, they have different absorption bands. This nucleic acid, they have UV contrast, and this red blood cell, they have visible contrast. So by just changing the wavelength of laser, you can differentiate them without any label. So as I mentioned, if you're using UV, then you can see nuclei, and if you're using visible light, then you can see blood vessel. So let me skip this simulation data and explain the final example. So we want to measure organoid using a photoacoustic microscopy. So normally tissue coloring method and fluorescence labeling was used to measure this thick, irregular 3D biosample. It has around 2 to 3 millimeter. So to monitor the structure of this organoid, you should do this process, tissue coloring and fluorescence labeling. And if the organoids undergoes these two processes, then their chemical property or physical property will be changed. So this is not real-time detection, right? For the drug screening, this real-time imaging is very important. So to solve this issue, we adopt this photoacoustic imaging technology. And also here we make this elongated beam for this very thick sample, and we want to make this 3D imaging using this like a needle beam of which is generated from metasurfaces. Yeah, so compared to the single focus meta lens, our meta lens can make this axially elongated beam. And then, yeah, this is PSF measurement without diffraction. It can propagate. It's like a needle. So compared to the simple aspheric lens or objective, our meta lens can be useful for this depth imaging, and also this simple leaf. We can see deeper using our meta lens. And also, we prepared two different organoids. So this is Parkinson's disease-oriented organoid, and this signal is coming from neuromelanin. This is kind of a biomarker for the specific disease, neurodegenerative disease. Anyway, using this needle beam and photoacoustic microscope technology, we can reconstruct this 3D organoid. And it is well known that this neuromelanin is spreading all over the area, especially in the midbrain. But in the forebrain, organoid in the neuromelanin, it is accumulated in a same area. And also, the another powerful point is that you can continuously monitor the organoid as you grow the organoid. So by if you see this different days of organoid, and also by growing the organoid, you can see this neuromelanin accumulation. So this is only doable using this photoacoustic microscopy because you don't change any chemical composition of organoid, where you can kill the you don't have to kill the organoid for the imaging. And this staining results show that actually we're gonna really see neuromelanin. This neuromelanin signal, actually this photoacoustic signal is coming from the neuromelanin. To certify that, we conducted this Fontana staining. And also this immunostaining shows that neuromelanin generating cells, we show that they have dopaminergic neurons, which is the source of the neuromelanin. All right. Yeah, this is a summary of my talk. So I explained 4 different technology. First one is cell monitoring using PrET, and also ultra-fast metaphotonic PCR for a single molecule sensor, and also this needle beam photoacoustic imaging for organoid. And these are the collaborators, Professor Luke Lee at Harvard Medical School, and my former PhD advisor, Junsun Wo, and my colleague in SKKU. And these are my student and postdoc. And thank you for your attention. And I'll be very happy to have your question or comments. Thank you.
Thank you so much, Professor Inki. So first of all, let's give a kind of applause for very nice talk.